Okay, let's do this example problem from the typer's book. And this involves blocks being pulled upward at different accelerations and velocities. The lower block is the same, it says. So what they mean here is the same mass. So all of these, let's say, are going to have a mass m. And the masses of the upper block varies. And then it's asking us to rank the force of tension. So in that case, like let's say that's an upward force. If we're talking about the force of tension on the bottom block, that would be, let's call it capital T. So as we look at this problem, we would want to draw a free body diagram. Now, it would look a little different for each of these blocks, right? Because some of them are not accelerating. So some of them are accelerating down or up. So if we, like, for instance, for case A, right? We would, if we're drawing a free body diagram of just the bottom block, then we would have acceleration upward. So we know that Fg down is smaller than the force of tension up, okay? So then, and we know also, right, the relationship between mass and the force of gravity, because we know that equation. And, you know, normally because this is a down force, we would put the negative signs in front. So we'd have like negative here, negative there, right? So then in that case, we know capital T is bigger than mg. Then in the case of case B, right, then if we were drawing this free body diagram, we would draw them to cancel out because we know that the acceleration is 0 for this case. So we'd have the same size, because remember that the mass is not changing. So, but then T is going to be smaller in that case. Okay, so these would be like same size. Right. So you already know, okay, that case A, the tension's going to be larger than case B. Now, generally speaking, like if you goof around with this, in a spring scale, I have a scale here to measure the tension. So I have a string, I have a mass here. When I yank it up, that's when the scale gets larger. The force measured on the scale gets larger when I accelerate up, okay? And then when I let the pressure off, that's when I notice that the reading on the scale goes down, because I temporarily kind of let the mass slow down. But let's do it mathematically. It just feels better to prove it. So in every case, if we're trying to like make a general rule here, we would know that the net force on the bottom block, right, is equal to its mass times its acceleration. That's Newton's second law. And net force is also equal to the sum of the forces, which would be capital T plus negative mg, because I'm sticking with an up is positive situation. Okay, now if A is negative, we'll just make sure that we plug in a negative number there. Okay, so let's solve this for T. We would just add mg to both sides, right? So we'd say T equals ma plus mg. If you want to get real fancy, you can say T equals ma plus g. And we just have to watch our signs here, okay? So in the case of A is positive. And remember, We already took care of the negative. G, like, don't worry about the fact this G is always positive. We took care of the negative over here. We already did that. So don't do it twice, okay? Don't make it negative twice. We already did that. So this is a positive 9.8 now. So if we were trying to solve for tension here, we would like do T is equal to M times 2 plus 9.8, you know, if we were trying to get numbers. Okay, so we have like a pretty big case here in A, because we're adding 2 to 9.8. So we know A is pretty big. So we've got like A plus G here for T equals here. Let me pause and erase some of the clutter. Okay, so in the case of A, we're going to have T equals M A plus G, right? And that's going to be a big number like 11.8, okay? In the case of B, it's just going to be T equals mg because A is 0. For C, A is downward, so that we would make that negative. So this would be T equals m times like negative 7.8, right? Okay. Then here for D, we've just got mg again, because we're going constant velocity. Even though it's going down, don't let that bother you. Same thing here, not moving at all, right? Not accelerating, not moving. And then the F is the same as C. So we've got T equals M times A plus G, but A is negative 2. So we just end up with 7.8. Okay? So then when we look at all of our numbers here, then we're going to have A being the largest tension, because you're trying to yank that string up. And you have to have the string has to win over gravity to get that block to accelerate. And then we have a big tie, so we have 3 mg's in here. So that would be B, D, and E. Okay, and then in the 2 downward accelerations are C and F. And so in that case, you actually have to let gravity win over the tension force in order for it to accelerate downward. So you get C and F being the least. Okay.